All right. Good afternoon, everyone. Welcome to the short paper session on scientific visualization, ensembles, and accessibility. I'm Han-Qi Guo from the Ohio State University, by the way, and we have 6 papers in this session. And each paper will have 7 minutes to present and followed by 2 minutes of a Q&A. You can ask your question on Slido or Discord or ask in person somewhere in the room. Right, and the first presentation will be given by Daniel Brown. His title will be about the color coding. Right, Daniel, the floor is yours.
Yeah, thank you very much for the introduction. So I'm Daniel Brown from the University of Cologne, and this presentation is about the color coding of large value ranges applied to meteorological data. The paper is the result of a collaboration between computer scientists of the University Cologne and the King's College London and meteorologists of the University of Cologne. Our motivation were meteorological data on the ice water content in clouds. These data sets contain large value ranges, which means their values contain several different exponents in the scientific notation. For example, ranges from 10 to the power of -7 to 10 to the power of -3, and even larger. So on the right, you can see the visualizations currently used as a standard by the meteorologists. In these gridded scatter plots, the time is mapped to the x-axis, the height is mapped to the y-axis, and the measurements of the ice water content are encoded by color. As a standard, they use viridis and rainbow color maps. Yeah, so the main challenge is to encode data with large value ranges by color. This makes the reading and comparison of values very difficult, as it can be seen in the example below. It cannot be said with certainty in which orders of magnitude the values of the marked region lie. The example illustrates that color maps developed in previous research work well for linear scale data, but show weaknesses for large value ranges. So in our approach, we split every value in its 2 parts, the mantissa and the exponent. We map every exponent to a different hue and every mantissa to a sequential scale of the respective hue. We call this order of magnitude colors, or short, OMC. So with the values encoded by our new color scheme, this is how the visualization of the meteorological data looks like. In comparison to the example from the beginning, the orders of magnitude that are contained in the marked region can now directly be seen. But the perceived borders between the exponents can also easily be perceived as large changes in the data. To access this problem, we implemented a variation of the OMC color scale in which we flipped the gradient of every second sequential scale. This leads to a much smoother transition between the exponents and reduces the perceived borders in the original version. We evaluated our approach in a user study. In this, we compared our 2 color scales with the current meteorological standard color maps, rainbow and viridis, and a color scale that was generated by the state-of-the-art tool Color Crafter that was provided by the literature. In total, 53 participants took part in the online study, from which 48% had a meteorological expertise. Other backgrounds were computer science, mathematics, and physics. All participants had a degree in their expertise. So we had 4 main tasks in our study. In the interpretation tasks, the participants had to read extrema and values as exact as possible. In the discrimination tasks, they had to compare extrema in 2 different data sets and had to compare values in 1 data set. Additionally, we measured the response time and the confidence of the participants in their answers. For the main results, we first have a look on the percentages of correct answers per task. On the one hand, OMC outperforms the other schemes in interpretation tasks. So in the reading of extrema, the multicolored schemes have significantly more correct answers than the sequential scales. In the reading of values, OMC shows significantly better results than all the other schemes. On the other hand, OMC shows comparable results to the best performing ones in the discrimination tasks. Additionally, our approach leads to significantly more precise identification of individual values. This can be recognized by the far smaller range sizes answered by the participants in the value reading task. Other results are the OMC color scale is among the best in response time in any task, but there were no significant effects at all. Our approach leads to a significant increase in the confidence of the answers, and there's no need of a meteorological background to understand our approach. In future work, we have to examine the color selection more closely. In this research, we didn't consider color vision deficiencies. Furthermore, it would be interesting to apply our approach to data from other domains or other visualization types. So in summary, we introduced a new color scheme to encode data with large value ranges. It uses a separate representation of the mantissa and exponent and shows better results in interpretation tasks while showing comparable results in discrimination tasks. Moreover, it doesn't need more time or methodological expertise to understand our approach. With that, I thank you very much for your attention. If you want to try our method, we implemented a Python library that automatically generates such order of magnitude color scales. Thank you.
All right, thank you, Daniel, for the very interesting talk. So we do have a couple of questions from the audience. So the first question would be, have you applied your method to three-dimensional data?
Oh, three-dimensional data is a pretty nice idea. So we didn't consider this in this research, so we focused on the meteorological data for this. But of course, as I mentioned, we want to apply this method also to other domains and other data types, so this might be a good idea for future work.
Okay, thank you. So another question is, how does your work relate to color map as opposed to multivariate visualization with data fusion by Park Wong in Ensembles 2022? I think this one is quite specific.
Okay. Can you repeat it, please?
Yeah, so there's a paper titled Multivariate Visualization with Data Fusion.
Okay, so I don't know the paper yet, so yeah, I will definitely have a look on it, and maybe we can discuss this on Discord as well. Yeah.
Thank you. I want to follow up on the 3D. Sorry, are there any questions you want to ask right now?
Yeah. Yeah, that's true. I think this is kind of a Beamer thing because we also calculated on the bottom. You see the calculated percepted distances between the exponents. So these are the delta E value, and there you see it's on the same level as the other ones. So, yeah. But thank you for mentioning. Yeah.
Right. Thank you for the question. So looks like we still have a question, but we have to move on. Maybe you can interact with the audience offline. So the next talk will be given by Marco in virtual. So we will first watch the video and then switch to Q&A.
Hi, this is Jens, and with me here is Marco. And we're going to present Volume Puzzle. This is a collaboration between Hamad bin Khalifa University here in Qatar, CERS4, and University of Turin in Italy. Segmented volumetric data has become popular in various application domains, like neuroscience and connectomics, where it is used to analyze connections between brain neurons. Likewise, material science uses it for the analysis of fibers or porous structures. Segmented volumes are obtained through labeling of microscopy image stacks or CAT scans. They are characterized by many segments, each of them exhibiting multiple heterogeneous attributes. Understanding spatial patterns associated with individual attributes or combinations of them is considered a challenging, complex, and time-consuming task. We thought this task was a bit similar to popular word puzzle games, in which players need to recognize word patterns in 2D letter grids. We therefore propose an interactive framework that we call Volume Puzzle. Volume Puzzle integrates various tools for spatial analysis and real-time exploration. This includes 1- and 2-dimensional transfer functions to map segment attribute values to optical properties for volume raycasting. We also propose a semi-automatic technique for computing 2-dimensional transfer functions based on attribute projection and a topological analysis of density functions. Our framework is based on a real-time volume raycasting renderer built on top of the mixture graph data structure presented here at VIS in 2020. This allows us to handle compressed mid-mapped segmented volumes, as well as immediate propagation of optical properties from attributes to volume segments. On top of our mixture graph rendering framework, we created various widgets to support the spatial analysis of volumes. Our framework supports 1D transfer functions offering piecewise linear interpolation of colors and opacities, as well as 2-dimensional transfer functions that enable concurrent mapping of 2 different attributes. In the latter case, both the color and opacity in the transfer function are obtained by a bilinear tensor product of 2 one-dimensional transfer functions. These 2-dimensional transfer functions are a key component of our framework. To obtain them, we begin with a complete list of attributes projected to a 2-dimensional space by means of dimension reduction such as principal component analysis, TSNE, or UMAP. This results in a 2D attribute scatter plot from which we compute a continuous scalar function using kernel density estimation. Many kernels can be used, and in our preliminary experiments we consider Gaussian kernels. Once we have a continuous density function, we analyze its topology using Morse-Smale theory. This gives us a way to detect and classify the critical points of the function. We use the method from Gerb et al. For a stable computation of the Morse-Smale complex. We then use the critical points to derive a geodesic interpolation. For each segment, represented by a point in the reduced 2-dimensional parameter space, we compute the geodesic distances to the corresponding peak and valley in the density function. We do so by computing the associated streamline through forward and backward gradient integration using a 4th-order Runge-Kutta scheme. We then use these distances to critical points to derive interpolation weights for colors and opacities. This allows users to only specify optical properties at the critical points of the scalar function and to provide a piecewise linear opacity function. The optical properties of all segments are then computed by interpolation. I now present some results for synthetic and real-world data. We first created synthetic volumes containing many spherical segments. Each sphere is assigned scalar attributes at random following a normal distribution. In each volume, we have then hidden a spatial pattern by modifying the attributes. The pattern can be revealed by selecting a particular combination of attribute intervals. As we expected, we realized that solving the volume puzzle through manual transfer function editing produces high cognitive load and is very time-consuming, even for those simple scenarios. In contrast, using volume puzzle's semi-automatic scheme, the patterns are revealed with minimal interaction and effort. We also tested 2 real-world datasets. The first one is an XCT dataset of fiber-reinforced polymer. Here, users are interested in finding spatial patterns associated with various fiber properties such as length, diameter, and orientation. For the second neuroscience dataset, domain scientists can use the system for analyzing spatial patterns formed by neural structures such as axons and dendrites. For the future, we plan to investigate the potential of the framework for the analysis of large-scale connectomics. In this context, shapes and sizes of nuclear envelopes, mitochondria, and axon bundles are of interest. We also plan to extend the system with brushing methods in the parameter and/or in the volume space, and to investigate potential extensions to three-dimensional projected spaces. Finally, we plan to customize the framework to other complex multivariate data volumes, such as ensemble simulations. Additional information about Volume Puzzle, we invite you to read the paper and to contact us. We thank you for your attention, and we conclude by advertising open positions in our lab and the upcoming World Cup here in Qatar. Thank you.
All right, thank you, Marco, for the presentation and joining us for the Q&A session. Let me ask you the first question. So you mentioned the
Good
next
afternoon, all of you.
Sorry, can you hear me?
Good afternoon.
Okay, so the first question is, how does the MSE-based method apply to higher dimensional transfer functions, right? So you now have 2D transfer functions. What happens, what will change for 3D and 4D or even higher dimensional transfer functions?
I would say that once we project to 2D space, we will still get a two-dimensional transfer function. We're not planning to have multi-dimensional transfer functions.
Okay.
I don't know if I got correctly your question. You asked, it's like we said that we want to get on 3D, but at the same point, we will use more or less the same scheme of Morse-Mail complex. So we will perform interpolation starting from the critical points.
Thank you. Are there other questions you can post on Slido? I have another follow-up question. So have you considered using continuous scatter plot to define transfer functions?
It's something that we plan to consider when we will deal with ensemble simulations.
Okay.
Actually, yes, it's actually a very good point.
Okay, thank you.
Thank you.
All right. Looks like we don't have other questions. And let's thank Marco again.
Thank you very much. And
so our next presentation will be given by Alexander. The title of the paper is Droplet Local Line Integration for Multi-Phase Flow.
Yes. Is it on? Thank you for the introduction. So my paper is about droplet local flow, and I'll jump right into it. Hope it works. Oh, now it does. Perfect. Yes, so streamlines, path lines were originally designed for single-phase flow. That means you maybe fill the whole domain and get your integral curves that way. For multi-phase flow, we are usually only interested in the flow within the droplets and not necessarily the flow around them. And there's a strong interdependence between the droplet local flow and so how it influences the droplet movement overall. So it might influence the change in droplet shape by having some kind of oscillating behavior. And so we want to be able to visualize this in a droplet local sense. For this, the path lines, they should follow the droplet local frame of reference. That means, as you can see here, we have then removed the translational and rotational velocities and have a view on how the flow is in relative to the droplet's movement. And we add glyphs for context so that you still are able to see what kind of information we removed from the original data. And let's start with defining what a droplet is for us. So we define a droplet just as a volumetric entity, so not very specific, and a droplet can be of any shape and size. And we have these droplets that move then over time, as a small example here, where we have 3 different time steps of the droplet's movement. And for this, we can define a single frame of reference per droplet and per time step, which consists of the translation and the rotation of the droplet itself. And if we use this information, we can fix this droplet in space so that it does not move anymore. And we have maybe a droplet that is fixed like that. And if we then compare this on how a particle in this droplet would move, we can see that we have some kind of droplet local flow visualization. So the trajectories can either be in a global or a droplet local frame of reference. So to get there, the first step is to modify the velocity field. We start with a velocity, general vector field for a droplet D. Then the first step is to calculate the translational velocity, which is just the integral, volume integral for the velocity weighted by the density. In a discrete situation, this would mean that we sum over all cells the velocities and average them to get the translational velocity. This is one velocity per droplet, so this is independent of the position in this droplet. However, for rotation, we compute it by using the inertia tensor and the total angular momentum. And here we have the velocity at a point is dependent on its position as it moves or rotates around the axis of rotation. And what we get if we decompose it like that is if we get our droplet local flow field just by subtracting the translational and the rotational velocity field from the original one. If we would now use this directly for traditional path lines, as here in the example where we have the initial value problem for the path lines, you can see that after one time step, those are droplet, the original path lines. So you see here how a path line is usually constructed. For simplicity's sake, we use here just an explicit Euler approach. And so the position of those particles we trace for the path line, they move with the droplet itself. And if we go now for to a droplet local path lines, we have to exchange the vector field that we put into the equation, and also we get different positions of the path line. However, if we do this just here simply by replacing the velocity field, we run into the problem that after a time step, that we have a wrong position in the second time step. This is due to the, if we just use it here low, I'm sorry. I think I skipped over a slide. I don't know how that happened, but sorry, to get back to that, is the velocity field, as you see now at the position x1, we use this position to sample the droplet local velocity field and bring this velocity to the original droplet. This way, we sample at the correct position in our droplet and get the correct velocities. However, in this case here, we have the problem that the droplet itself is rotating, and thus we have to account for this rotation of the droplet again by back-rotating the velocity in the original droplet. So this is, again, a small fix of this equation. So we need to calculate the whole droplet rotation to use this information to get the correct velocity in the original droplet for a droplet local flow. And if we just do this over and over again, we can see that here, if we compare the original path line in black to the one in red, that's just the droplet local path line. We can see that now instead of a huge arc, the path line might go in a vortex-like. Sorry. Am I over time already? So yes, then just to get you a small example, here we apply this to a few droplet sets. So we have the traditional path lines and streamlines and the droplet local ones. And for example, here you can much better see the internal flow behavior. In the first one, you see it's just like moving away, and in the second one, you can see some vortex structures. We have a bit of the same findings for the path lines, and we can also do this for streak lines, but the example here is not that interesting, so I'll skip that over. For the glyphs, we just add these information by adding arrows for translation and rotation, and also a rotation axis. So yeah, we have a dynamic and a static frame of reference, because in the normal version, we have the issue that if we recompute the frame of reference in each time step, and for it to be a bit more intuitive to understand, we also provide a static frame of reference, but then we need to explicitly track droplets. So in conclusion, we provided a method for vector field decomposition to get the droplet local flow, integrate path and streak lines in there, and provide glyphs for context. And this works very well for small and medium-sized droplets, and also has some other interesting application possibilities. Limitation is that collisions cannot be handled really well, but still a bit. And as future work, we would do this try to do this in situ, because we don't need to do resampling for the vector field, which is quite nice if we do this in situ directly then. So with this, I want to wrap up, and I welcome questions.
Thank you, Alexander. Very nice work. I don't see questions yet, but I will start with one. So in case the droplet start to split or merge, how do you correctly handle these particle locations?
Sorry, again.
In case a droplet splits into two, or two droplets merge into one, how do you correctly handle the particles?
So it depends a bit on if you're using a dynamic or a static frame of reference. But the separation process is usually not an issue, because if we have the correct frame of reference from the previous time steps, and we know can directly use it. For the collision, it's a bit more difficult because now if we have a static frame of reference, we don't know where this droplet comes from. This is not ambiguous because there are two original droplets, and you would need to apply kind of both of these frames of reference which were computed in the first time step. But it works for dynamic frames of reference, but it is, well, you have to look at it a bit more closely. So it's, you can use our method, but it's a bit harder to interpret in this situation, as collisions are always a bit difficult to handle. And yeah.
Yeah, that's very challenging. For the sake of time, let's thank Alexander for the very nice presentation again. The next talk will be given by Hao Yu from the Ohio State University. He will talk about B-spline representation for path lines.
Thanks, Hanqi, for introduction. I'm Hao Yu Li from the Ohio State University. Today, I'm going to present our work, efficient interpolation-based path line tracing with B-spline curves in particle datasets. So particle tracing is a widely used technique in vector field visualization for its effectiveness in revealing scientific features. And path line, which is a particle trajectory traced in time, is especially important in the analysis of time-varying vector fields. An established method to compute path line is to use numerical integration. That is widely applied on grid-based vector fields. However, for particle datasets derived from simulations such as smooth particle hydrodynamics, directed adoption of this traditional method might not be promising. Numerical integration can be very expensive on particle datasets. The reasons are twofold. In order to perform interpolation of velocities for a given particle, neighborhood search is needed. However, since particles don't have a predefined connectivity, like grids, this can be quite expensive. So ideally, we want to perform as few numbers of searches as possible. And on the other hand, frequent velocity interpolation is required. For example, for southern Runge-Kutta, 4 interpolations are needed, making numerical integration very costly. In an effort to improve path line tracing efficiency, there's an alternative interpolation-based path line tracing method proposed by Chandler in 2014. Instead of performing multiple velocity interpolations in numerical integration, their interpolation-based path line tracing method only interpolates once per time step on particle displacements. As a result, number of interpolations amounts to the number of time steps. However, this method can still be very expensive when applied to particle datasets with high temporal resolution. So to tackle this challenge, we propose a new method to represent each path line as parametric curves. And by interpolating the control points, the number of interpolations can be effectively reduced. Now we illustrate our path line representation. We start with the original particle positions in the path line. And we fit the B-spline curve along the trajectory. Then this path line of particle positions are replaced by the control points. If the B-spline is constructed carefully, we can store a significant smaller number of control points than particles, while preserving a relatively small error. Next, we'll introduce our B-spline fitting strategy. As we all know, not factoring B-spline curves specify the control points to use for query parameter U. Therefore, in order to reduce the fitting error, We would like to have more nodes around the places where the path line structure is more complex, such that more control points are placed here and we can have a more faithful reconstruction. We use a node placement method proposed recently by IEEE. A future function is designed to define curve complexity, such that the values of this function change faster when the fitting data are more complex, and more nodes are placed at those regions. In this example, we observe that when the curve structure exhibits more complexity, the future value changes faster and more nodes are placed. And when the curve is less complex, we have slower value change and then less nodes are placed. So having decided node positions, we fit the control points using least square method, minimizing the distance between the particle positions and the curve. After all the particles are represented as B-spline curves, we now can perform interpolation on the control points. Suppose at step 2, we start tracing a particle at time tau and position rho. We identify some closest neighbors. In this example, we choose 2. And then we interpolate its next control point, P of R, from the next control points of the neighbors, P of D. We repeat these 2 steps until the last control point is reached. We demonstrate our advantage in chasing time reduction comparing to the baseline method by Chandler. The timing recorded given both baseline and our method have relatively small fitting error, which will show next. We observe that our interpolation time can be at least 10 times faster with 100 control points after the data is fitted. The interpolation time decreases as we decrease the number of control points used to represent every path line. Having demonstrated the effectiveness of tracing time reduction, we show the path line tracing quality comparison with the baseline when we use 100 control points. The left figure reports the IMC with respect to the ground truth path line, and the right figure shows the visualization of these curves and ground truth. We observe a slightly lower RMSE using our method and overall similar tracing quality. So in conclusion, we proposed an interpolation-based path-line tracing approach on particle data represented as B-spline curves, and our experiment results show reduced computation for path-line tracing while we preserve similar quality compared to the baseline method. That is all for my presentation. Thank you for attention, and also thanks for the funding agencies. I'm glad to take any questions. Thank you.
Thanks, Hao-Yu, for the very inspiring presentation. We have one question from Chris Johnson. How does this compare to the Oslo algorithm about knot insertion?
Compared to what?
There's a knot insertion algorithm for B-splines.
Ah, I see. So knot insertion method for B-spline can, it's actually we use automatic knot placement. Because if you cut the B-spline curve recursively, you may not have a best knot placement in that case. So maybe you will need more control points in that case to represent the B-spline. Okay. So maybe that will be less efficient.
Okay, thank you.
Thank you.
Another question is, have you compared with, considered using other parametric curves?
Yes, we actually tried Bidel curves and other kind of parametric curves. Also for the same reason, automatic knot placement in B-spline can be can make us using less control points that make the algorithm more accurate or more efficient. Thank you.
Right. Thanks, Hao-Yu, again for answering all of these questions. Let's thank the speaker again. So the next presentation will be Dominic. His talk will be about visualizing confidence intervals for critical points in 2D scalar ensembles.
Thank you. We are interested in the critical points of piecewise linear scalar fields on two-dimensional simplicial grids. In this case, critical points can only occur at the vertices of the grid. Depending on the function values at neighboring grid points, a point can either be a maximum, minimum, saddle, or regular point. We can use this definition, for instance, to mark the maxima of a scalar field. How can we analyze such points in an ensemble of fields? Of course, we may display the juxtaposition of all those fields with their maxima highlighted as before. However, as the ensemble size grows, this quickly becomes incomprehensible. We therefore require some way to summarize this information. For instance, we could depict the relative frequencies of maxima to estimate their occurrence probabilities. A drawback of this is that the quality of that estimate strongly depends on the ensemble size. This picture, for instance, is computed from only 10 members of an ensemble. Computing the same picture from different members of the ensemble will produce varying results. The goal of our work was to capture those uncertainties. Sticking with the example of maxima, we note that each grid point is either a maximum or not. The number of occurrences of a maximum at some grid point can thus be described as a random variable following a binomial distribution with parameters being the number of fields in which we examined if the point is a maximum and the generally unknown probability for a maximum at that point. Assume, for instance, that we examined 25 fields and that the probability for a maximum was 0.6. This results in the depicted distribution for the number of maxima at the grid point. We can use relative frequencies to estimate the true probability for a maximum. Computing this estimate from several draws of the binomial distribution, we obtain results that vary around the true probability indicated by the black line. Our goal is to compute confidence intervals for Pmax to capture the extent of this uncertainty. That is, we seek two random variables describing the upper and lower bounds of an interval of probabilities that will contain the true value of Pmax with probability larger than some confidence threshold gamma. In our paper, we use the Jeffreys interval for this purpose. This uses Bayesian inference and the Jeffreys prior to find that the likely distribution for Pmax, given the number of observed maxima at the grid point, is a beta distribution. For instance, if we observed a maximum in 18 of the 25 fields, this would result in the depicted distribution. We can then use the quantile function of the beta distribution to compute tails that will contain Pmax with some low probability. For instance, to compute an 80% confidence interval, we find tails that will contain only 10% of the density. This results in the shown confidence interval. If we repeat this process for each draw, we will find that on average 80% of the computed intervals will indeed contain the true value of Pmax. The previous considerations can be applied analogously for minima and saddles. At each grid point and for each of those three types, we therefore have the point estimate and the confidence interval for the occurrence probability. This totals in 9 values at each grid point. To visualize all of them, we propose the following glyph-based approach. First, we partition the glyphs into 3 regions spanning the same angle. Then, for each type, we plot circle segments with areas proportional to the upper boundary of the confidence interval in light colors. On top, we plot circle segments with areas proportional to the lower boundaries in darker shades of the same colors. Finally, we draw a black arc with enclosing area proportional to the point estimate. From those glyphs, one can read 2 kinds of information. First, a large portion of a darker color and a large black arc indicate a high probability for a critical point of the respective type. Second, a large portion of a lighter color indicates a large confidence interval and there is a high uncertainty of the predicted probability due to small sample approximations. We applied our method to ensembles with different numbers of synthetic fields. This picture shows the results obtained for 2 different ensemble sizes and a confidence level of 95%. For the smaller ensemble on the left, most points don't feature a dark inner portion of the glyphs. That is, it cannot be ruled out on a 95% confidence level that the probability of the point to be critical is 0. Some points, however, contain dark inner parts. We can be confident that they will be of the respective type with non-negligible probability. While all points on the left show large portions of lighter colors, indicating a rather high uncertainty of the prediction, the results for larger ensemble on the right shows much smaller confidence intervals, indicating a more trustworthy prediction. We additionally applied our method to a dataset from climate research. This picture shows the most dominant mode of variation in sea level pressure over the North Atlantic during the northern winter. The depicted dipole pattern is characteristic for the so-called North Atlantic oscillation, which is a driving factor of the European winter weather. We analyzed the critical points of this field in different climate ensembles, simulating different global warming scenarios to investigate how climate change impacts the depicted centers of action of the NAO. Those pictures show the northern center of action defining the NAO for the first and last 50 years of the simulation. We can make out a slight northward trend of 2 regions of minima. Here we see the southern center of action for the same time frames. We can make out an even more pronounced shift of maxima towards the northeast. In conclusion, we presented an approach for the computation and visualization of confidence intervals for the occurrence probabilities of critical points in ensembles of piecewise linear scalar fields. It provides the user with visual feedback on the trustworthiness of critical point predictions, whereas most existing methods ignore uncertainties that arise due to small sample approximations. On a real-world dataset, we could reiterate previous findings regarding the impact of climate change on the North Atlantic oscillation. The proposed approach operates locally at the vertices of the grid. This offers good scalability and parallelizability of the algorithm. On the other hand, this has the drawback that the result will depend on the grid resolution, as the probabilities will converge to 0 with finer grids. We therefore plan to search for methods that also take into account the spatial autocorrelation in the data to identify regions of critical points that describe the same topological feature. The probability of those features would then be more independent of the grid resolution. Finally, we wish to thank the Deutsche Forschungsgemeinschaft for funding this project, and of course you for your interest in our work.
All right, thanks, Dominic. So we have one question from audience, which is how well does this method scale to 3D and also larger scale data?
Well, the computation of the confidence intervals scales well because in 3D, for example, you just gain more different types of saddle points. Of course, you would have to deal with the clutter when you display the glyphs in 2-dimensional space, so I guess that would be the largest problem.
All right, let's thank Dominic again for the presentation and the Q&A. Let's welcome Marina. The next talk will be given by Marina about the visual exploration of active system ensembles.
Yeah, hi, I'm Marina Evers, and I will present our approach ASIVIS for the visual exploration of active system ensembles to define characteristic measures. So let's first look into what active systems are. Active particles are particles that can take energy from their surroundings and use it to propel themselves. One example are, for example, bacteria. If those active particles are then fixed in their positions on a crystalline grid, we obtain an active crystal. Here, we can describe the orientation of each particle by a 3-dimensional particle vector. If we now want to describe the whole system, we can concatenate the individual particle directors and obtain a multidimensional feature vector. So in case of 7 particles, as we have here, we obtain a 21-dimensional feature vector that varies over time. These simulations in active systems strongly depend on the input parameters. So common input parameters we have in this example are the distance d between the individual particles in the crystal, as well as the propulsion mechanism driven by a parameter called beta. So how can we now analyze such ensembles, and how can we analyze the dependence on the input parameters and define some characteristic measures to describe the individual ensemble members? So for this purpose, we propose ASIVIS. That's an approach with the goal to define measures to analyze the system's dynamics. Here, we support two different measures or two different ways of aggregating. The first one is to define an aggregation delta of t for each individual time step. This then results in a single scalar value for each time step, which in the next step can be aggregated over time, such that each ensemble member can be described as a single value. So now the challenge is, how do we define these measures? And that's supported by our tool. Basically, our approach is based on an experience in working on active system ensembles, and we derived some tasks and abstracted them. But for more details on this, I would refer to our paper and directly present the workflow for this work. So the first step would be to get an overview about the data and get an understanding on what's happening in the simulation ensemble by investigating single runs. That's supported by 3 different detailed visualizations, namely the animations you've already seen on the slides before, a line plot showing individual components of the particle directors, as well as a scatter plot matrix. After having some overview about the data, the next step would be to interactively define the measure for each single time step. So here we include an interactive programming interface directly into our tool, where the domain expert can directly include his own definition. After defining a measure, of course, one wants to observe it, and this can be done in a so-called time plot, where each ensemble member is represented by a line over time, and the y-axis basically shows the user-defined measure. Now, after several iterations, one wants to define a measure delta head that aggregates over time. And here we use a similar interface as for the time-dependent definition. Then in the next step, of course, we also want to visualize the result. And here it's especially important to visualize the dependence on the parameter values. And for this purpose, we propose to use a heat map visualization. When we assume a 2-dimensional parameter space, we can span the heat map by the parameters and use a color coding to encode the user-defined measures. So basically, for the definition, we have a bottom-up approach that we can see here, and each step normally needs several iterations. But after suitable measures are found, the next step would be an analysis on different levels of detail. So here, the first step would be, again, to observe the aggregation measure and also the distribution in parameter space. And the heat map supports interactive selection such that the user can select some ensemble members and visualize it and investigate its evolution over time. And to understand how the different states differ from each other, another important aspect is the possibility to select single ensemble members and investigate them in the detailed visualizations. To get a better idea on how this tool was used, I will now present a use case. Here we observe an ensemble that contains 30 ensemble members of up to 6,000 time steps. And the goal of this ensemble was created in a physics project. And the goal was to define an order parameter to investigate different states between the different active crystals, where states refer to the temporal domain. So here we see 2 different kind of representative ensemble members, and we already can see they behave quite differently. One contains more or less periodic motion, and the other one, at least I can't see any pattern. It seems pretty chaotic. Now it's of special interest to define this order parameter, and it needs to fulfill some criteria. So that's why we included this interactive definitions. So after several steps, we came up with a definition of an order parameter to investigate for each multidimensional feature vector in time, how close does this feature vector come back to the respective previous feature vector. And one point that is important to note, and one characteristic of this measure, is that it becomes 0 if it's periodic, because in this case, the trajectory in the 21-dimensional space always comes back to the original point. So we used this definition for the time-dependent measure, and for the aggregation over time, we used the mean to preserve this characteristic of getting to 0 for periodic cases. So if we now investigate our distribution in the parameter space, we can see that, especially here, for beta equals roughly -3 and small values of d, we get a periodic behavior, which we can see because the values are really small and going down to 0. To better understand what's happening in this ensemble, the next step would be to get a selection of the simulation ensemble members and observe it in the time plot. Here we can roughly see 2 different groups, but we can also see one ensemble member that somehow jumps in between. So if we now investigate the single ensemble member in detail visualizations, we can observe that before this point, where it performs a jump, it shows a somewhat periodic behavior, or at least close to periodic. And for larger time states, it shows a completely chaotic behavior. So to conclude my talk, we presented an interactive definition approach for characteristic measures in active system ensembles. Our approach is highly generalizable to other domains because only the detailed visualizations are really domain specific but can be adapted easily. The findings I presented in the use case actually resulted in an article in the physics domain, but of course our approach also has some limitations. So the higher dimensional parameter spaces are currently not supported because it strongly, depends on having a two-dimensional parameter space, which was completely sufficient for this use case. But for multi-dimensional parameter spaces, which are also quite common, it would be good to use more sophisticated approaches, like, for example, a hyperslicer visualization. Yeah, so thank you for your attention, and I'm happy to answer some questions.
Thanks for the presentation, and there isn't a question yet, but I have a quick question. So I only see like 7 particles in the visualization. So how would you like to scale for a much larger set of particles?
So in principle, like our visualization approach scales quite well. The detailed visualizations, of course, on some point they're not suitable anymore because, for example, this line plot would get completely cluttered. The problem here, why we used only 7 particles, was more the computational cost for the simulations. And also the other approaches, the aggregation visualizations also scale really well, and the computations for the aggregation measures strongly depend on the definition, so it's hard to say.
Mm-hmm. All right, thanks. And we don't have other questions. Let's thank Marina again. And the next presentation will be given by Mengjiao Han remotely.
Hello, welcome to the talk. My name is Mengjiao. I'm happy to present our paper, Accelerated Probabilistic Marching Cubes by Deep Learning for Time-Varying Scalar Ensembles. The work was done alongside awesome collaborators, Tushar M. Asawil, David Puckmeyer, and Chris R. Johnson. Uncertainty of ensembles has been extensively studied via visualizing positional uncertainty of level site. One solution is using subcategory plot, which shows the isocontour for each member of the ensembles. A more popular method is the probabilistic marching cubes, which calculates the level site probability for each grade across all the ensemble members. The probabilistic marching cubes solve the occlusion and clustering problem of the subcategory plot. However, because it uses multicolor sampling to draw the samples from multivariate Gaussian distribution, the probabilistic marching cubes technique is extremely expensive. In our paper, we proposed the first study of uncertainty visualization using deep learning techniques to predict the positional uncertainty of level site for time-varying scalar ensemble data. We showed that our method can predict the level crossing probabilities accurately. Moreover, our method is up to 170 times faster than the original probabilistic marching cubes with 0 computations, and up to 10 times faster than the parallel computations. In our approach, we generated training samples from the first T time steps and evaluated using the following time steps. The process follows the approach in the probabilistic marching cubes algorithm. For one time step of ensembles, capital Y0 to Y3 represents variables at the vertices of a 2D grid. Each Y is a vector containing the variables of all ensemble members. To compute the level site probability for a given cell, the mean values and covariant matrix of the ensemble data are computed. We refer to mu as the mean values of each grid vertex. It's computed by averaging the data across all the ensemble members. Then the 4x4 covariant matrix is computed from the ensemble members to capture the pairwise correlation between the data at each grid vertex. Our samples are randomly drawn from the multivariate Gaussian distribution using the means and covariance matrix. Given an SO value S, the level crossing probability for a cell is then computed as K divided by R if the level site passes through K samples. For our current study, we only selected fixed SO values from 0.1 to 0.9 with interval of 0.1. These SO values are used in both training and testing for simplicity. Finally, each training sample in our training set represents one grid cell with a vector of size 16. The first 4 values are the mean values. The next 10 values are from the covariance matrix. Since the matrix is symmetric, we only keep half of the matrix. The last 2 values are the SO value and the target level crossing probability. The network architecture of our method, built with multi-layer perceptron with the sign activation function. The network takes the mean values, the values from covariance matrix, and the SO value as the input, and outputs the predicted probability. The L2 loss between the predicted and targeted value is calculated. We evaluated the network performance and compared our proposed deep learning-based approach with the original probabilistic marching cubes algorithm. We demonstrate that our proposed method is accurate and efficient by analyzing it on ensemble dataset from the climate data library and the RISC simulations performed at the COST supercomputing lab. The wind and temperature datasets has 45 days. Each has 15 ensemble members. We use the first 17 days for training. The RISC data resolution is a bit larger. We use 15 days and first 10 days for training. Each day has 10 ensemble members. We use a dual RTX 3090 GPUs for training and the desktop with Intel Xeon CPU and the NVIDIA Titan RTX for evaluations. Here we show the visualization of the predict results using our method compared to the ground truth using the RISC dataset. Our method can produce the results indistinguishable from the ground truth. For the wind and temperature datasets, our method also can generate identical predictions. The original probabilistic marching cubes algorithm was implemented with serial computation. In our paper, we first accelerate the algorithm by parallel computation. With parallel computations, the performance increased about 19 times. By comparing with our deep learning method, we found that our method can further accelerate the parallel probabilistic marching cubes up to 10 times. In addition, the performance of our method didn't impact by the number of multicolor samples. The same result can be found with the wind and temperature dataset. Our method can speed the performance up to 10 times and doesn't decrease by the number of multicolor samples. Due to the time limits, please read our paper for more information and results. In conclusion, our deep learning-based approach is the first study applying deep learning to uncertainty visualization. We predict the positional uncertainty of level sites for time-varying scalar ensemble data. Our method is accurate and accelerates the original probabilistic marching cubes up to 170 times with the serial computations and up to 10 times with parallel computations. In the future, we plan to extend our approach to 3D datasets, enhance the flexibility with varying SO values, and generalize the approach across varying datasets. Thanks for all the funding supporters, and thanks for listening. Hello.
All right, thank you, Menjiao, for the presentation and joining us remotely. I will start with a question. So you mentioned you want to extend this to three-dimensional data, and I wonder about how difficult is it to apply to unstructured mesh data with no direct way of applying convolutional neural network.
I think the difficult part is how you can generate the training samples for the unstructured data set. So if we can come up with like how we calculate the probabilistic marching cube algorithm with the unstructured data set, I think it's very easy for the training part. And also this is the benefit of using the deep learning method. It won't depends on like how your data set is. It depends on how your training samples.
Thanks. Are there any questions? All right. Let's thank Manjao again for joining us. And we have the last presentation by Nihant.
Good afternoon, everyone. I'm Nihant, and I'm a project scientist at the National Center for Atmospheric Research. And this is the work that I did in collaboration with Becca Hathaway, Tiffany Foreman, David Bailey, Mareka Holland, and Matt Ramey. We're all like scientists and educators who work at NCAR and UCAR. So to begin with, data visualizations rely on visual encoding of data, and consequently, they pose accessibility barriers for folks who don't use vision as their primary means to consume information. Secondly, the issue about accessibility in data visualizations is an underexplored topic in visualization research, with only a handful of papers that have been published in the past. And lastly, the perspective of individuals with disabilities is something that was identified as, it was identified to be largely missing from the visualization literature from a recent research article. So to address some of these limitations, we designed this research study to identify some socio-technical barriers to accessibility by interviewing individuals who are blind or vision impaired. And second, we also provide some recommendations which emerged from analyzing the data from the interviews with these individuals. And we address the following research question, like what are the experiences of students and professionals who are blind or vision impaired in geosciences with accessing information presented through data visualizations. Now, we understand that data visualizations are ubiquitous in all disciplines, but in order to isolate any domain-specific findings, we picked one discipline, which is geosciences. And geosciences was picked partly because it was identified as one of the least diverse STEM disciplines. Now, for data collection, we interviewed 7 individuals who are blind or vision impaired. And coming to the structure of the interviews, all the interviews were semi-structured in nature, and the questions were open-ended. The questions explored the importance and impact of data visualizations at various stages in their career, as well as like the techniques that they've used to access these data visualizations. Now, the questions touched on 3 aspects of their lives. So we looked at K-12 education, higher education, and their professional lives. As for data analysis, we employed Braun and Clark's reflexive thematic analysis, and we followed the 6-stage sequential iterative method for reflexive thematic analysis. Now, please refer to the article for the details on the analytical process and the reasoning behind these theoretical assumptions. So this whole process, it resulted in 5 key findings and 3 recommendations. Now, in the interest of time, I'll be going into 3 of those key findings and 2 recommendations. Now, the first finding pertains to the limited availability of tools for research, and this is a technical barrier. Now, while there have been significant technological advancement in the use of alternate sensory modalities, such as like tactile graphics and other means of exploration, participants found that those approaches had significant limitations that prevented their application in research. And they've also stated that seeking assistance from a sighted person with subject matter knowledge in that area of study was currently the most effective means of accessing this information presented through data visualizations. Now, so they made statements related to the need for tools that enables them to explore the data independently. The next theme captures the barriers related to accessing visualizations published by their peers. Now, there exist guidelines for including alternate textual descriptions for images, and these have sort of evolved to be the industry standards. However, participants mentioned that the majority of the visualizations that they've encountered in academic works, such as seminars and presentations in conferences, they lacked alternate text. So this theme revealed the lack of awareness among the peers about the importance of having alternate text to academic works, and also to adopt common best practices to make graphical information more accessible in academic works. The next theme explores the degree of impact and the degree of impact of these barriers at different career stages in their lives. So participants who were in their later career stages mentioned that they received sighted assistance often through staff that were employed by their institute, or by staff that were employed by funding that they received through certain research grants. Now, both these things are not something that early career professionals and students have access to. And coincidentally, this also happens to be the phase when participants mentioned that they moved from consuming information from data visualizations to actually producing data visualizations for communication. So overall, this highlights the critical role played by higher education in determining the enrollment and retention of students with disabilities in different fields. Now, moving on to the recommendation. The first recommendation is related to raising the accessibility awareness among the peers. Now, this is meant to address the absence of basic accessibility features such as alternate textual descriptions in works published by academia. And so it also puts emphasis on the importance of understanding the accessibility guidelines, and this is something that all of us as a community can do to make the space more inclusive. And the second recommendation is related to providing access to underlying data. Now, all the participants who I've interviewed were like highly proficient with computers, and many have devised their own techniques to explore data. Examples of those include like having small code snippets to sonify data, as well as techniques in which they would take the data and run it in a tabular form through a Braille refreshable display so they can feel through all the values. Now, these techniques won't be useful unless they have access to the underlying data. And this is the underlying data that was used to produce the visualization. So to that end, like participants identified that even providing access to the underlying data would be a significant step towards improving the accessibility of visualizations. And this also requires minimal effort from the presenter's view. So in conclusion, we've identified socio-technical barriers and have some recommendations to improve the accessibility of data visualizations. And these things have emerged from the interviews with people who are blind or vision impaired. Now, there are some ways in which we can address these accessibility barriers. So the first thing to the social barrier is to address the first social barrier. It's to have some basic understanding of how people with vision impairments use screen readers. And like with this knowledge, we are able to identify like how we can effectively make things like alternate text included in graphics. And moving to the next two technical barriers, from our conversations, we found out that there was a distinction between exploratory and explanatory data visualizations, as well as techniques used for authoring data visualizations versus consuming information from data visualizations. So paying attention to these nuances can help us create techniques that are more effective in making visualizations accessible. And lastly, although there are things like sonification that were very popular among our participants, especially for making sense of time series data, but they often don't scale well to multidimensional data. So this is another opportunity for us to expand, and there's an opportunity for research on that front. With that, I thank you, and I'm happy to take any questions.
Thanks, Nihan, for the presentation. We don't have a question from audience yet, but I have just a quick question about how would the conclusion change if the audience would be the general public instead of professionals?
Yeah, that's a very good question. And that's the distinction between like exploratory and explanatory visualizations. So most of our participants mentioned that like these alternate sensory modalities, such as like 3D printing and like there are some other tactile means, they work really well for visualizations that are geared towards general public. They fall short in research mainly because of some limitations that I've mentioned in the article, that for things like you can't make a 3D printed stuff for exploratory visualization and then throw it away and make a new one. So factors such as resolution and like having a refreshable equivalent of a visualization becomes more important for things like research.
Thanks for the answer. Right. That concludes the whole entire session. Let's thank all the speakers again, and please follow up with all the speakers on Discord and offline. Thank you.